Okay, welcome. Next time we meet, there's going to be an examination, and the material, if we're going by our book, will be all the material up through and including section 4.7. I will not, however, ask you any questions over section 4.6, which is the functions of several random variables, which we haven't got into yet, but we have covered actually some of the stuff in 4-7. So the book, the test itself, of course, is closed book, closed notes, but you're allowed to have, of course, a single 8.5 by 11 sheet of paper on which you can have anything you would like written. Okay? Any questions on the exam? Yes?
I noticed on one of the sample midterms you have written that there's a included sheet of equations and such.
Mm-hmm.
Is that going to be also on this test? Or?
No. You didn't ask in time. I have the examinations already made out. However, I will tell you that except for basic equations, you won't have to know the density function for the Erlang random variable and such. You should know the Gaussian, the exponential, probably the Cauchy. You should, if I give you either the Chebyshev or the Markov inequality, I'll give you the equation for it. I think one of the questions, the answer has an error function in it, an ERF. There's no reason that you need to give me a numerical value. You can leave your answer in terms of ERF with a parentheses around it. That's fine. I'm assuming that you have the wherewithal, given the time and resources, to be able to determine what the ERF of 1 is. So hopefully that'll be useful. Shouldn't know the definition of the gamma function, the basic probability density functions. I would include, again, in those the Gaussian, the Cauchy, the exponential, and then the common discrete random variables being the Poisson binomial random variables. Negative binomial, no, don't worry about that one. Somebody in the front row went. Had you spent the time memorizing the negative? Oh, you have your sheet already in the negative binomials on there. Okay, I'm sorry. Should I tell them they should put the negative binomial? Okay, you might see the negative binomial. Okay, you feel better? Okay, good. Okay, any additional questions about the mechanics of the test? What I'm going to do after we're done talking about the mechanics and the rules of the test is that I'm going to open it up for any questions that you might have over the material that we've covered that we can answer in here. This would include homework, questions on concepts within the material. I would advise you again when you study to study by the overhead slides and the homework. And if material was not addressed in the homework or the overhead slides, you won't see it in the examination. For example, you won't see in the examination, I think, some of the different convergence criteria which were covered in the book. We simply don't have time to cover all of those things. Okay. Any other questions on the administration? By the way, I should say that if you are taking the course via EDGE, that you're, of course, welcome to take it on site. My preference is that you take it at the same time that the class does, which is Thursday from 10:30 to 12:25. We'll cut it off at 12:25. And if that is not possible, then I'm going to ask that you take the examination so that it at least overlaps the examination here. So you'll take the exam and you'll end it in the middle of the exam, or you'll start the exam in the middle of this exam and end it otherwise. In all cases, the examination for EDGE students needs to be proctored, and I think that's it. Also, if you need special conditions for your work, such as time and stuff, please check and clear it with Hongbo. He's doing all of the coordination of giving the exams off campus in special cases. Okay. Any other questions about the administration of the test? Yes?
Any chance we could get more time?
More time than the 2 hours?
Than Thursday, I mean.
More time than Thursday. Ooh. No? It's nice of you to ask. I think my preference would be, unless you can give me a compelling reason to put it off longer.
Because you told us you wanted 2 weeks.
No, I never said 2 weeks.
You did.
Hongbo said it.
Hongbo said that.
Hongbo, okay. Yes.
No, I'm sorry, I've gone back to the video stream for the first session, and you did say 2 weeks.
No. It's been my policy for the last decade to give 1 week. I hope I didn't say 2 weeks. I hope I didn't say. And indeed, if I did, it's a little late, two days before the test, to do it. Another factor is the logistics, in the sense that we have the proctors all lined up in the EDGE program, and that would require realignment of those. So my preference would be to go ahead with Thursday. Okay. I sense hostility. And if I did say 2 weeks, I misspoke. Okay. If I did say 2 weeks, how many are in this class? 40? 41. Oh, 40. Okay. Hongbo, how many are in the class?
I think it's around 50.
Ooh, okay.
But less than the number.
Okay. I was going to say that if I did misspeak, I would buy you all a latte, but that's too much. I'll give you all 10 extra credit points. Of course.
Are we grading on a curve?
Yeah, we're great. So you'd be better to go with a latte. I'm sorry. Okay. Any additional questions? I'll think of a way to make it up to you, at least in a token manner. Yes.
We're only having one midterm or two?
You'll probably get 2 midterms. Is that okay?
Is that final?
Yes, and a final. And homework. Okay, any additional questions on the administration of this? Okay, with that, let's open it up to questions which you might have concerning the homework or the material. Sometimes, by the way, when you get in the material, you get to a point and say, man, I don't know enough to ask a question, okay? And if you're there and you got the guts, go ahead and admit it, and I'll try to break through the wall for you as far as getting you to understand the things. In other words, I'm trying to encourage that there will be no stupid questions. Yes, ma'am?
Problem 443.
Problem 443.
Part A, B.
What page is that, please?
261.
261?
Oh,
Okay, the problem in 42, you're asking question 42 on page 261, is that right? 43. Daggone it, I just worked 42 in my head. Okay, I'll see if I can. Okay, 43. Okay, what I'm going to do is actually move this and do some work on the overhead camera. So let me see if I can. It's a problem with high-tech stuff. Excuse me. Still getting over the anthrax. Okay, 443 is that we have x1. Uh-oh, my zoomer isn't working. There it is.
The Zoom button's not working, so you have to direct me.
Okay, not even if I push it really, really hard?
Not even.
Okay. Okay, the zoom button isn't working. Well, just make it so that it's clear. 43, we have x sub 1. I draw small, by the way. X sub 1 is uniform on the interval from 0 to 1. Can everybody see that? And x2 is uniformly distributed on the interval of from 0 to x2, or x1. In other words, we take a random variable here, and whatever this random variable is here, we generate a new random variable. And x3 is uniformly distributed on the interval from 0 to x2, etc. So clearly, as we do this, we're going to have x3, this is f sub x3 of x, we're going to have x3 being less than x2 being less than x1. Now, we can't draw a density function which looks like this. Why? Because the density function is a function of a random variable. Density function cannot be a function of a random variable. A density function is totally deterministic. So therefore, this is rather f of x2 of x given x1. So f of x2 of x given x1 is given by the relationship that we have here. In other words, we're given x1. x1 is something which has been determined. So this is a conditional probability density function. Then we use Bayes' relationship, which is that f of, and by the way, this is x1 is equal to x2. I'm sorry, x1 is equal to x1. So this then becomes the conditional random variable for this problem. Therefore, let's see, what do they ask for here? They ask for the joint probability density function for x1, x2, and x3. And the way that we would do this is use the results in problem 41. Now, in problem 41, we are given that the density function from a conditional probability point of view is equal to f sub z of z given x and y times the density function for y of y given x times, we're running off the screen here. No. Yeah, well, good. Okay, yeah. F sub x of x. This is the result from equation 41. So, in our case, instead of calling these x1 and x2 and x3, can't we call them x, y, and z? Can everybody follow that change without too much of a problem? Thank you. If I don't mind. No, I don't mind. They just brought me up alternate pens saying that my pen was too thin for them. Okay. Now look at the difference between their pen and my pen. Here's my pen, here's their pen. See? Big difference. Okay, what we've just done is we've said that f sub y given x, we said that this was equal to a uniform density function over the interval from 0 to x as a function of y, so it has a value of 1 over x over this interval from 0 to x as the conditional density function. So this is f sub y of y given x. In a similar fashion, f sub z of z given y and also given x, because we need x in order to get y, turns out to be a density function which looks like this as a function of z. It goes from the interval 0 to 1 over y, or 0 to y, and has a value of 1 over y. You agree with that? Yes?
I don't know why you need to be given x. It seems like if you were given y, then you would know everything about x that you need to know about.
Yes, but subsequently, the way that I understand what you're saying, but in the description of the experiment, you need y, let's say you need x in order to get y. That you can't get y without knowledge of x, because because y is conditioned on x, and so therefore z is conditioned on y, which in turn is conditioned on x. Okay? Then the f sub x of x, of course, is the original random variable, which is something which is just on the interval from 0 to 1. Hence, obtaining the entire, using these three formula and substituting into the relationship which we have on the top here, gives us the total density function for the random variable x, y, and z, the joint density function. Now one has to be careful here, because you'll notice that x here let's see, that the value of y must be less than x. So if we could go down here, f of x, y, z of x, y, z is equal to the product of these things, which is 1 over x times y. However, we must have the random variable y must be less than the random variable x, less than or equal to the random variable x, correct? Because we have chosen that random variable. And the random variable z must be less than or equal to the random variable y. So therefore we have the density function being equal to 1 over xy over this region in the xy plane, and of course the lower limit for z is 0 and the upper limit for x is 1. So therefore we're constrained to be within this wedge, if you will, in the unit box. So this then is the solution to the problem. Does that answer your question? Okay. Anything else on this problem? I didn't go through all of the things. I found the joint PDF of x.
On 41 and 43, I have the solutions, but I can't read them.
You have the solutions, but you can't read them.
Right, it's like a scan resolution kind of thing. And so I don't really need you to go through all of 43B, but if I could read the solution, then I could probably figure it out.
Let's see, 43B. The answer to 43B is yes.
Cool, all right.
Okay. Except this doesn't, wait a second, something's wrong here. This is chapter 4, 443. Yeah, something's wrong. There's a mismatch here, isn't there? Did anybody else notice a mismatch here? Between the problem and the answer in the solution book. This is the first time that I've noticed this.
Well, I can't read the answer, but they may or may not be.
Yeah, it definitely is a mismatch. They have Gaussians and all sorts of things in there which have nothing to do with this particular problem, because the x's are distributed uniformly. Huh. I think that the solution you have is just a total...
I don't see any Gaussian.
There's no Gaussian solution I have here. It looks fine.
The solution you have there looks fine?
It is difficult to read, but you can sort of make out what.
Could somebody offer me their solutions? I can't walk. Yeah, I guess I can. I thought I was tethered to something. Okay, first of all, you see 43A is exactly what I said it was. Here we need to carefully determine the limits of the integrals. I'll read this for you. For a given x3, x2 varies from x to 1. For a given x2, x1 varies from x2 to 1. I'm sorry, I can't read this either. Okay, let me attempt to work it for you.
If you could rescan it and repost the solutions to those two problems, then I would be.
I'll ask Combo to do that. Okay. Yeah, I'm not sure what happened there. Is this true for all of the scans, or was this particularly just a rough one?
The midterm that you posted is also not readable.
Okay.
One of the midterms.
Okay, so I'll ask Hungbo to repost 40, give them to me, 42,
41 and 43.
42, 41, and 43.
42 wasn't assigned.
Okay, I'll do that just for your recreation. And also the midterm.
You said he doesn't have the hard copy.
Oh, he's right. He's right. I'll have to give that to them, or you'll have to do without the midterm. So I'll see if I can get that posted for you. Okay, any other questions then on the homework? I think I probably have the old midterm, and I can post a PDF file of it, so that would work. Except it won't have the solutions with it. So. Can I answer questions on the old midterms? We'll find out if I can, yes. It would be embarrassing if I couldn't. I do not have the old midterms in front of me, so
I've got another question on the homework.
okay, well, let's do this, and then she's coming up here,
Okay.
and then we'll anyone that I want. She says anyone with the tag. Okay. Well, let me ask this. Is there anybody that has any other challenge, any specific questions on the homework? Actually, these came out okay. What's wrong with these?
That one is good, the other one.
Oh, the other one's bad. Okay. Okay, I will say that on this, midterm number 1, we got a little bit further the last time. So, yeah, you should be able to do 2. C4 is material specifically excluded from this test. So 4 is not, 4 you would not be asked on this test, neither 5. That's the summation, that's a future. Well, let's see, wait, hold your taters. No, 5 would be fine. That's simply the product of, yeah, we've done that in the, we've done this in the class. No 4, but 5, yes. Yeah, 6 is a line mass sort of problem. Okay, which one would you like me to talk about then? 2, 5, and 6. Okay, problem 2. Let's take a look at problem number 2. Did you say 3, 5, and 6, or 2?
We're just clarifying something here.
Okay, 2 you want me to do, right? Okay. Okay, so we have in 3D space, a uniform random variable of x, y, and z. So here is x, here is y, and, whoops, that's not y. Y is over here. There's y, and here is z. So there's a three-dimensional function, and what we have is the random variables x, y, and z being uniform and independent over the interval from 0 to 1. Therefore, if we actually do the probability density function, we get a cube, and this cube is a 1 by 1 by 1 cube. And within this cube, the probability density function is equal to 1, and it's 0 outside of the cube. Do you agree with that? Oh, you don't? Oh.
Shouldn't it be a 2 by 2 by 2 cube?
It's negative.
Oh, you're right, you're right. This is from -1 to 1. You're exactly right. I didn't read my problem. Okay. I would have at least got partial credit on that one. You're right. I didn't see it was from -1 to 1. So it's -1 to 1, -1 to 1, -1 to 1. So therefore we have a... okay, we have a cube, and here's the origin. Okay, right there's the origin. So we have coming out here, y coming out here, x and coming out here, z, and this is 1 and -1. So yes, it turns out to be something which is on the interval from 1 to -1. Okay, so it looks like this. Now we're going to let, so this, what I've plotted here is the density function for x, y, and z. And the density function for x, y, and z is equal to, what's it equal to within this box? It looks like a 2 by 2 by 2 box, so it looks like 1/8 within the box, correct? So it has a value of 1/8 within the box and 0 outside. Because the total volume of the box is 8, and we must have a total, if we integrate everything, we must have a total value of 1. So therefore it has a value of 1/8 in the box and 0 outside of the box. So that's the situation we have. Now we have z, or we have a new random variable, r, which is equal to x squared plus y squared plus z squared. Motivation for this, by the way, is in that ideal gas place where we have the x, y, and z velocity. We have the density function for the x, y, and z velocity, but we're not interested in that. We're interested in the speed, which is the magnitude of the velocity. We would do a random variable transformation of this type. Of course, in an ideal gas, we wouldn't have a uniform density function, but nevertheless, the idea, I hope, is there. Now, we have this problem, and we see that the maximum value that r can have is what? Root 3? That's the biggest value that r can have. And what's the smallest value that r can have? 0, correct? In case everything is at the origin. Do you agree with that? So therefore the range of the random variable is over the interval from 0 to root 3. We're not sure exactly what it's going to look like, but once we do compute the density function for r, it is going to only have a mass which is over the interval from 0 to root 3. Okay? So that's what we're asking in problem A. Find the cumulative distribution function for r only over the interval 0 from c is equal to 0 to 1. Okay, so the next problem is as follows. Given the density function for c, or for r, I'm sorry, that of course is equal to the probability that the random variable r is less than or equal to r, which we know is equal to the probability that the following is true. I'm sorry, this should be a C, shouldn't it? Is okay? Now, the beauty of this is that this relationship is recognized as a sphere, as indeed it should be. And it's a sphere with a radius of C. So therefore we have a box, and inside this box we have a sphere. Don't forget the little bubble. Give it a three-dimensional perspective. We have a sphere inside the box which has a radius of C, and of course the box has a relationship between -1 and 1. Now you notice I only ask you specifically to find this over the interval from C is equal to 0 to 1. Can you see why from the geometry I would ask that? Because over that interval, that sphere is totally inside the box. If C got a little bit bigger in the box, the sphere would start peeking outside the box and the integration would get a little messy. So we just wanted to do something very, very, very easy. And of course, the volume of the sphere over this interval, the volume of the sphere is 4/3 pi r cubed, right? And the value within the sphere is equal to what? 1/8, since it's uniform throughout the sphere. So this is equal to the density function for C over the interval from C to 1. Now, in order to compute the entire density for the random variable, we would have to figure out what happened when the sphere was peeking outside the box and when the box was totally inside the sphere, and it's a little more complicated problem. But this specific case, I only ask you for a result which was straightforwardly evaluable. Okay? Yes?
I think I understand how you got the 1/8 again.
Okay, the 1/8 comes from the fact a density function must be scaled so that its total volume is equal to 1 in 2 dimensions. In 3 dimensions, if we integrate over everything, we have to get a value of 1. Now in 3 dimensions, you don't have a volume anymore. I don't know what do you get when you integrate in that fashion. But this means our original density function, when we integrate over this box, we have to get a value of 1. Now, we know that since the random variables are uniform within the box, or within the cube here in this case, that the total volume of this cube is 8. 2 times 2 times 2. So therefore, if I integrate this density function, if I integrate this cube over the entire space, I get a volume of 8 times whatever value is inside the cube. Well, that value must be so that the total integral is equal to 1. So therefore, the value of the cloud inside here, and we can think of 3-dimensional density functions as kind of clouds, the value within the box is 1/8. Okay? So that is where we got that. Now, another way to do that, if that intuition fails you, is to go back and recognize that these are independent random variables. And if we have f sub x of x, it looks like this, right? It has a value of 1/2 over the interval from -1 to 1, correct? And how do we get the 3-dimensional density function? We do that smearing thing, except in 2 dimensions. We smear it in x, smear it in y, and smear it in z. So we would actually get the density function by multiplying 1/2 for x, 1/2 for the y component, and 1/2 for the z component. Okay, I'm getting crinkled brows. This is equal to the following relationship, right? I think we're going to have to close the door just while classes are dismissing here. Do you agree that this is true? Because they're independent? Well, what is this equal to? That's equal to 1/2. What is that equal to? That's equal to 1/2. What's that equal to? That's equal to 1/2. So the total value is equal to 1/8 as long as x, y, and z are within the cube. And they're 0 otherwise. So that's where the value of 1/8 comes from. So we have a cube, and inside of the cube it has a value of 1/8, and on the outside it has a value of 0. So when we integrate in the sphere, we get the volume of the sphere times the value within the sphere, which is 1/8. So it's 4/3 pi r cubed times the value within the sphere, which is 1/8. Does that answer the question about the eighth? Okay. Any other questions on this problem? Okay, what was the other one you wanted to have worked? Is 3? Which one? 5? Okay, problem number 5 on the take-home test. The idea is that we have a random variable, and this is the summation. And each one of these random variables is IID and distributed as an exponential random variable. What we showed in class was the characteristic function for the sum, this was in the lecture notes, was equal to the characteristic function for one of the random variables raised to the nth power. Do you remember us doing that in class? Okay. So that indeed is the case that we have here. Now the only thing you have to figure out is what the characteristic function is for this random variable. I would not have you memorize, well, for the exponential you should be able to figure it out. But it's equal to lambda over 1, or lambda minus j omega is the characteristic function for x. So the characteristic function for s is equal, of course, to this simply raised to the nth power. And if you were to have a table of characteristic functions before you, which they did for this test, you would go down that characteristic function table and you would say, ah, this is the characteristic function for the Erlang random variable. I would not give you this problem unless I gave you the characteristic function table for these things. Okay? So you would look at this and say, aha, this is the characteristic function for the exponential. If I raise it to the nth power, that is the characteristic function for the Erlang random variable. And just to recognize from the table that indeed this is an Erlang random variable. Okay? So this would be a difficult problem if I had required you to memorize this, but I won't do such a thing. I would give you a table in such a case. Who asked that question? Is this okay? Okay.
So when you say evaluate the exact PDF, that means just say it's Erlang?
Well, you would get to here, and then I think to actually answer the question, you would have to write down the density function for it, which you would look at on the table also. So it'll just be looking at a lot of tables. Okay, any other questions? On the examination? Did that answer enough for you, or do you want some more? Well, they're not doing anything else.
I got a question on the homework.
Okay, let's do some homework, and then if we have
Okay,
time, we'll come back
okay.
to that. Is that okay to you?
Yes.
It's 4.50. When you set up the integral, I wasn't sure where the absolute value of y are.
Well, let me ask you this. Can you go ahead and start with the magnitude of y? Let me be sure that I understand your question. Your question was, where did the absolute value y come from in the quotient formula for the quotient of the two random variables?
My question is, what motivated someone to put the absolute value of y in this integral? When I tried to do it, it looked
Within this integral, what integral?
the very first one on the solution of 4.6. F sub z of z equals the integral from
No,
negative-
don't read it. Yeah, you better read it. 550?
450.
450. Same thing. Okay. Man. That's the reason that isn't working. It's the wrong solution book. I brought the wrong, okay. Yeah. I brought the wrong solution book with me today. It was the solution book for something else. So no wonder the solutions didn't make sense. They are not misprints. It's a totally different book. Okay, so I'm going to have ask if I could borrow this relationship. And for a quotient, here is the expression. I think we derived this in class, didn't we? And this is if z is equal to x over y? Okay, thank you. I'm gonna keep this just for a second. And your question is, why does this magnitude have to be here?
Oh, so that's something that we derived in class?
Yes, it is something that I think we derived in class for when x and y were non-negative. But let me tell you why this has to be a magnitude, at least from the viewpoint of a sanity check. If this was negative, there's a good chance that this integral could go negative, and you'd have a density function which is negative. So just from a sanity check sort of point of view, we better have this magnitude around here, because I think you can see that if we didn't, it wouldn't be difficult to cook up a case where you get a negative density function over here, which indeed we can't. Okay. It also comes from the fact, I believe this comes from the fact that that the y dy was actually a substitution for dz. And anytime you perform a variable substitution of this sort, you need to put the magnitude here, because the dy is sensitive if you're integrating to the left or integrating to the right, and you have to be careful to make sure that if you integrate to the left or integrate to the right, that in either case it's a non-negative value. Okay. So I don't know if that answers your question. At least, hopefully, it makes sense that it's a magnitude there. Maybe you don't understand the details of why it's there.
Yeah, I just need to look back at the derivation.
Very good. I think actually, in fairness, the derivation that we had did not do for all values of y. I think we had both x and y non-negative. Okay. What one would have to do is go back and do that same derivation more generally, and you'd find out the magnitude of y is there. Okay. I believe it's also in the text. The derivation is in the text, isn't that right? Of the quotient. Okay, I'm almost certain that I saw it in there. It's one of the examples?
Example 4.34.
434. So it's worth that. Okay. Is that all for this question? Okay. Any additional questions then? Number 17. Okay, number 17. We have a random variable x, which has a density function that looks like this. And then we have the output y is equal to x plus some noise. And the noise is a Laplace random variable. It looks like this. Find the probability that x is equal to k given, and that y is less than or equal to y for k is equal to 1. So therefore, we're asked to find the corresponding densities here. Now, what's interesting about this is that if we look at the density function for x and y, the density function for x and y is going to be the density function for x. You know what? I better look at the solutions. Do you have the solutions? For 441? Thank you. Okay, they go through it with a law of total probability. What I was going to do is actually to generate this equation, because there's some things that immediately shout out at us here. One is that x and n are two random variables which are independent from each other. So how do we get the density function for y? We convolve these two, correct? What happens if you convolve something with a delta function? You get back the thing center where the delta function is at. So if we were to actually look at the density function for y here, if we look at the density function for y, we would have this Laplace down here centered at -1. And then we would have that Laplace also centered here at +1. And we would add these two together to get the density function for y, which would look something like this. So that's kind of nice that we can use this convolutional property immediately here in order to get the density function for y. But let's then look at the problem that they ask for specifically. The probability that x is equal to 1 given, let's see, that y is less than or equal to y. Okay. Probability that y is less than or equal to y given that x is equal to 1.
Look, it's a given. I think it's the joint probability.
Yes, it is. However, what we're going to do, let me look at their methodology here. Oh, I see. Okay. Following the solutions, they decide to express this in terms of a conditional probability. So with this, we can do, for example, for I is equal to 1. We can compute, I'm sorry, say again?
Should be into multiplication. Multiplication or?
Yes, you're right. Yeah, you're right. Yeah, it should be the multiplication. Thank you. So for I is equal to 1, if we're given that x is equal to 1, what is the density function? What is the density function for y given that x is equal to 1? Well, it's equal to exactly the density function before, except that the density function is shifted to be centered at 1. The Laplacian is shifted to be centered at 1. So therefore, in order to compute this, this density function in here, we have to compute the area here, and this area will be the probability that y is less than or equal to y, given that x is equal to 1. And we can compute that. However, the integral is a little bit sloppy, and I don't want to spend time going through the details of the integral, because the integral can either, if the integral is before 1, it's one thing. If it's greater than 1, it's something else, right? So, but this is something that we can compute. And from this, then, we can also compute the probability that x is equal to 1, of course, is equal to a half. So we can compute these two, and if we multiply these two together, we get the probability that this is the probability that x is equal to 1. Now, x can either be a plus 1 or a minus 1, and with equal probability. So therefore, the probability that it's equal to 1 is equal to a half. Okay? So the probability that y is less than or equal to y, and big comma, and x is equal to 1 is equal to the product of these two. So it's equal to this times this, whatever this is. And this, of course, is equal to a half. So it's a half whatever value that we can compute up there. In a similar fashion, one can compute the probability that y is less than or equal to y, given that x is equal to minus 1. Exactly the same thing, except that the conditional density function for y now is centered at minus 1. And this is the density function for y, given that x is equal to minus 1. So therefore, we would integrate, in order to get the conditional density, we would integrate in this manner up to, I guess it's y, up to a specific value of y. And in a similar fashion, we got this conditional, we would be able to get the conditional, the probability that y is less than or equal to y, given that x is equal to minus 1. And then from this, we could compute these probabilities also for x is equal to plus and minus y. That then, I think, takes care of part A. Is that right? 17. Yes.
That's fine now.
Okay.
That's no problem understanding the 1/2 part, so
Oh, okay.
I can get the rest.
Now, they did say in B, find the marginal probability density function of y. We could either do that by adding these two together using the theorem of total probability, right? We could add the x is equal to 1 and x is equal to minus 1 together to get the total probability, and then the total probability density function, and then find the marginal. But probably the easiest way to do the marginal of y, which is the density function for y, I think, is to simply do that convolution. And then what's the answer to C? C should be intuitive, actually. If we're given y is greater than 0, which is more likely, x is equal to 1 or x is equal to minus 1? What do you think? Yeah, 1, right? Just due to the symmetry of the problem. If it's positive, it should be 1. And you can go ahead and work that out and work the numbers out, but I think the answer is relatively intuitive there.
If you ask questions like that on an exam where there's a pretty obvious intuitive kind of answer, I mean, are written out answers like,
yeah, but
it
put
should
down,
be 1 because blah, 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 blah.
yes,
And
express your intuition so I know it's not a guess. Okay. For example, if you drew this and say, yes, it's obviously equal to 1 because of the symmetry of the problem, I would probably say, yeah, they got it. Okay. Whose was this? Thank you. And please, this is an engineering class, not a math class, so you're allowed to do that sort of stuff. Let's go ahead and take our break. Meet back here when the big hand's on the 7. Okay, let's return and ask if there's any additional questions or amplifications to any of the material or the homework. Yeah.
The problem 4.1, we're shading the areas, and then it asks if it's a product form.
Or of a product form. of a product form means that the regions can be represented as separable, as being separable, I think is the term that we're using, right? Yeah. It is, but separable in this sense, in terms of interval, means it's a separable function, but the functions that we're dealing with in x and y are binary, 0 and 1. Since if you think about 0 and 1 sort of functions, and you take a 0, 1 function for x, say for example you have a 0, 1 function for x here, and you have a 0 to 1 function for y going in this direction, and you were to look at the actual xy plane, you would find out that if you smeared this here and smeared this way, that this would be, you would get this result. Okay, this I believe is what the book refers to when they're talking about product form. So it is something like separable, except in the product form it means these intervals can be written as intervals smeared out in the x and y direction, which kind of means that we're looking at binary functions, 0 and 1 functions, is the way I like to think about it. So does that answer your question? So the question is given one of these particular plots, is is any of them separable? Just looking at this, I would think that B, if you have your books, by the way, this is 256, that B would be separable. I think C is, let's see, is C separable? Huh? Why is B separable? B is just looking at the interval of e to the x is what? Less than or equal to 6? I'm sorry? Oh, less than 6. Okay, so that means that x is less than the log of 6, right? Which means that if we look at this as a function of x and y, that we put the log of 6 here, and that it's all of these points, correct? And so this, in terms of separable functions, is equal to a function like this for x and a function which is all 1s for y. And if we multiply these two together, we get that wedge. So this would be separable. Okay? I don't know, C might be separable and I might be separable. I'd have to look at it more in detail. What does the text say about those? I is separable. What about C?
That's like when you just did on the board, and I read the
Oh, it is? Okay. So C is separable, and I think the rest are not separable. Just eyeballing them. No, I guess F would be separable. No, it isn't, because Y can take on either negative or positive values. Okay. Okay, did that answer the question about the separability and the meaning of that? I'm not sure who asked that.
Just sort of talk more in terms of basics what separability means, rather than just sort of go through some examples.
Okay, what does separability means? Let me talk about what I mean in terms of separable functions. We talked about this a little bit, but if you have a separable function, let me not even do it in terms of density functions. Let me do it in terms of just a regular two-dimensional function. This is a separable function. It's a function which can be written as the product of two other functions. And in general, g of x, if we have just a general function, it can be written as the product in an n-dimensional space of g sub k of x sub k. This is a separable function also. Now what's interesting about this is that not all functions are separable, clearly. In fact, most functions aren't. If you were to look at an image, for example, in 2 dimensions, and an image is a good example, by the way, of a two-dimensional function wherein white corresponds to a value of 1, and opaque or black corresponds to a value of 0, and the gray levels correspond to intermediate values. But if you look at most images, they're not separable. What's interesting, though, is that all images can be written as the summation of separable functions. In fact, you can take any function and you can write it as the a summation of g, say, how could I do this? Let's call it alpha sub k of x times beta sub k of y. And if you sum over k, you can always find a summation of separable functions which will give you the original functions, always. Okay. Well, now this is a product form here. What I'm saying, this is not a product form, but it is the superposition of a number of product forms. Okay, so this is a summation of a number of product forms. And what I'm saying is that any arbitrary two-dimensional function can be written as a superposition of separable functions. Sometimes this summation is infinite, in which case it doesn't help you out very much. But nevertheless, this is always the case. And in higher dimensions, g of x can be always written as the summation of k of the product. Oh boy, I'm getting too many subscripts here. Alpha sub k, no, I guess not, x sub k. Summation, I got to put an n here, an m. So this is the general statement for separable functions in multi-dimensions. You don't have to worry about this for this particular course, but this is an interesting result, which is sometimes useful in multi-dimensional signal processing, the separability issue. But this is separable in 2 dimensions. This is separable in n dimensions. And we talked previously about viewing this as smearing the one-dimensional function into the higher dimensions. In 2 dimensions, for example, it's like smearing the x function this way, smearing the y function this way, and multiplying the two together. And that's a nice way to visualize it. It's the way that I visualize it, yeah.
If the joint PDF is a separable function like that, and you can do the algebra to get the two separate, does that tell you that the variables are independent?
Yes.
Okay. Yes.
If a joint PDF is separable, then the random variables are independent. And you can show this, you can actually prove this by recognizing that a sufficient condition for independence is that the joint is a product of the marginals, right? And if you can make it separable, you can always lump coefficients and constants in with each one of the terms so that they integrate to 1. Each one of the individual component terms, the x term and the y term. Then you take out the x term, that's the marginal for x. You take out the y term, that's the marginal for y. And it does become the product of the two. So yes.
So that's an if and only if condition then, right?
Yes. Yes. It is an if and only if condition. That if you have a marginal and it's the, if you have a joint and it's the product of the marginal, then the underlying random variables are independent. Not only in 2 dimensions, but 87 dimensions. Typically, when we talk about IID random variables, which we normally like to think of as occurring from repeated experiments, those are often modeled as independent random variables, IID random variables, so that we can indeed talk about the joint being the product of the marginals. Any additional questions?
The light bulb problem in chapter 3. Problem 152.
So light bulb problem in chapter 3, problem 152. Oh, I love light bulb problems. We actually did this with the probability that x greater than t was an exponential. And we actually went over in class this problem for the, not the probability given here, but for the exponential probability, and that's where we show if a light bulb worked that long without burning out, it was still good as new. Okay? This is not the situation that we have here. That exponential model is the only one which gives newness. What is really interesting is that there's some models wherein if you use the whatever it is that you're testing, if you use it for a certain time, then if you've used it like for a week, chances are it's better than it was when it was new. Because you've weeded out the infant mortalities. You've weeded out the weak links that in the production process that would cause an early failure. Very interesting results. In fact, a lot of IC chips have reliabilities which are measured this way. Okay.
The exponential, for example, that means that the probability that it's still working at time 9, given that it was working at time 1, is the same as the probability that it's working at time 8.
And 0.
And 0.
Yes.
Okay.
Yes. It's a really interesting, peculiar result that when you first see it, it raises your brow. But again, I like to get back to this idea that I'm probably twice the age of most of you. I hope not bigger factor than that. But the chances that I'm going to die today are about the same as you dying today. So our failure rate as far as today is about the same. So that model is good, not over our entire lifetimes. You couldn't say that of somebody that was 107 years old. Their chances, well, they might not get through the day today. But as far as within a period, an interval of time, yeah, that's a pretty good model. It is a pretty good model. So it's like anything. It's like a linear model of a nonlinear system. You look at the linearization and you realize it's only good under certain conditions. It's the same thing with this reliability. Yeah, it's a really neat model and it gives you kind of neat results, but please be sure that when you apply it that it's applicable to the correct sort of situation. Okay, let's take a look at this.
Fail or they don't, as opposed to degrading. So a light bulb either is working or it's not.
Oh, I see. So the question is, do we have various degrees of degradation? In classical reliability theory, no, that isn't the case. I haven't kept up with reliability theory on the. I haven't kept up with it recently, but I'm sure that there's models where they talk about degrees of degradation. But you would have to define those. You would have to define those degrees of degradation and contingencies for obtaining them. Yeah. I think the binary model is a lot easier, don't you? So. One could talk about a fuzzy model. How many have heard of the concept of fuzzy and fuzzy probability? If you're interested, we offer a course in neural networks next quarter where we will also go into fuzzy logic. And fuzzy logic, fascinatingly, is another way to measure and to model inexactness, which is very separate from probability. Fuzziness, for example, could be used to measure the degradation of an item. So you could have fuzzy reliability, which would be interesting. I'm sure somebody has done it. They've applied fuzzy to everything else in the world. I'm sure they've applied it to reliability. But fuzzy, by the way, measures not probability, it measures possibility, which is totally different, because all things that are probable are possible. Do you agree with that? All things that are probable are possible, but all things that are possible are not probable. Right? It's possible that I could end my lecture in the next minute, right? But it's not probable, is it? Okay? So fuzziness, some people say, is the measure of uncertainty measured from possibility, whereas what we're looking at in random variableness now is measuring uncertainty in terms of probability, and they are totally different concepts. Sometimes they merge together conceptually and are very interesting. They also are used by Eastern, many proponents of fuzzy logic say that Eastern cultures are more easily grasp the concept of fuzziness than Western, because many times that they can actually hold contradictory concepts in their head, which fuzzy logic allows, which the 0 to 1 logic doesn't allow. If I were to tell you that the classical liar's paradox, if I were to tell you, I never tell the truth, would you believe me? Well, if you believed me, I just lied, and I always tell the truth, right? You follow? Okay. So this is, it's a meta statement. It's a statement which refers to the statement itself, and you get into all sorts of very interesting philosophical paradoxes which aren't resolvable by classical Aristotle Western sort of logic, but which are answerable in fuzzy logic, which is more Eastern, even though it was fuzzy logic was formally invented in the U.S. in '65 at Berkeley, of all places. Okay, let's talk. Why did I get off in that? Oh, I was pitching my course, 523, next quarter. Neural networks, and we're going to study fuzzy logic and genetic algorithms, evolutionary programming, which is a way to find answers which is modeled after evolution. It's really fascinating. Many things, such as the field of artificial life, springs from evolutionary computation. Everybody gets a 4.0 in my other course, not this course, but 523. If you take it, get a 4.0. Oh, this is on video streaming. Just kidding. Okay, let's go back to 152 here. Okay, 152. Here we have this probability model, the probability that x is greater than t. By the way, this many times is referred to as a reliability model. And it's a reliability model as a function of x as a function of time. And notice something interesting. It's actually 1 minus the distribution function for the random variable. Because 1 minus this is the probability that x is less than or equal to t, right? Isn't that the definition of the cumulative distribution function? So the reliability model many times is said to be equal to 1 minus the cumulative distribution function. So just like the cumulative distribution function goes from 0 to 1, the reliability function goes from 1 to 0, meaning when you start using something, you're 100% certain it's going to work, but if you go for 1,000,000 years, you're 100% certain it's going to die. It's going to be dead in 100 billion years. So the reliability model is the antithesis, an opposite sort of measure. So this is 1 over 1 plus t, and it's for positive values, so we multiply it by a unit step here. Got to zoom. No, you can't do it. You got to zoom. Okay. Ooh, good. Okay, good. Suppose the 3 new light bulbs are installed at time is equal to 0, time is equal to 1. All light bulbs are still working. Find the probability that at least one light bulb is still working at time t is equal to 9. Okay, in order to do this, let's just use one light bulb. 3 light bulbs are too hard to fathom, right? So let's use one light bulb. So what we want to find is the probability that x is greater than t, given that x is what? X is greater than 1. Because we know the light bulbs are working at time 1. So we know that they didn't fail between 0 and 1. We know that they're working at 1. So this then becomes a conditional probability statement, which is the probability that x is greater than t and x is greater than 1, divided by the probability that x is greater than 1. Did I get it right this time? Yes. So this being the case, let's take a look at this result. We have the timeline here. We have the timeline. There we go. Okay. Maybe if I used a less mushy pen. And we have an arbitrary value of time 1, and we have an arbitrary value time t. And we're asking ourselves, what is the probability that x is greater than t, and, that's what this comma means, and x is greater than 1? Correct? Clearly, the x is greater than t is an interval subsumed in the x is greater than 1 as long as t is greater than 1. Correct? So as long as t is greater than 1, which we know that it has to be, this probability is equal to the probability that x is greater than t. That whole numerator becomes this relationship, and the probability that x is greater than 1. Sorry, no equality here. Do you agree with that? This, by the way, is true no matter what reliability model that you use. That we haven't imposed anywhere the equations that we have yet. But now we can impose the equations. This is the reliability of the random variable x at time t divided by the reliability of the random variable at time 1. Which if we substitute in the definition that we had, was equal to 1 over 1 plus t over 1 over 1 plus 1. So it looks like it's 2, 1 plus t. So that is the new probability. This is the probability that the lifetime will be greater than t, given that the lifetime is greater than 1 for that random model. Excuse me. Does that make sense? Okay. So is that better or worse, by the way? It's better, isn't it? So this is one of those things, if we use it for a unit, yeah, it's better than when it started. And we think of that again, of killing out the weak ones in the production line when we did it off. Now, this is, by the way, for one light bulb, right? And let's call this, just for fun, let's call this P, okay? Now, what we're asking ourselves is, what is the probability that at least one light bulb is still working at time t is equal to 9? Well, the probability that x is greater than or equal to 9, given that x is greater than 1, is equal to 1/5, right? And if we ask ourselves, what is the probability that at least one light bulb is still working at time t is equal to 9? 1 out of 3, this is actually a Bernoulli experiment, right? We take 3 Bernoulli trials, we put 3 light bulbs on duty that are still working at time is equal to 1, and we find out how many successes we have. So therefore, we simply use this probability with repeated Bernoulli trials, which is described by what random variable? Binomial. So we incorporate this into the binomial random variable for n, number of trials is equal to 3, and k, which is the number of successes, is equal to, let's say, at least 1. Well, we would sum up k is equal to 0, which means 0 have failed. Sum up the k is equal to 0, k is equal to 1, and k is equal to 2, which is exactly the same as 1 minus putting in the k is equal to 3. Classic binomial sort of problem. Would you like me to elaborate on that at all, or does that make sense to you? Makes sense? Okay. So this actually is a problem which is broken into 2 parts. The first one is a reliability of a bulb, and then the second one is recognized that putting these number of bulbs on test is equivalent to doing Bernoulli trials of success or failures, and you're asked at the end of the test time, what's the probability that there's a certain number of successes or failures. And so it becomes a binomial random variable using the probability that you generated in the reliability statement. Did this answer the question?
I understand understand the 1/5, but in the solutions, they have a 4/5. And I'm not sure
In
where.
the solutions, they have a 4/5. Where do they have a 4/5?
That's the inverse of the probability of being less.
Oh, yes. Yes. See, the probability that it will still be working is 1/5, so the probability it's killed is 4/5. Yeah. So it's 1 minus that.
If the probability of failure is 4/5, can you cube that? And then 1 minus that is probability that at least one
Yes,
still
you
work.
can. Let me repeat that in case it wasn't picked up by the microphones. You can take the probability of failure, which is 4/5, you can cube it, and then subtract that from 1, and that gives you your answer. Okay, additional questions then? No more questions? Okay, well, thank you for your attention. We'll see you Thursday.